Welcome to day 3 of Next. I am so excited to see so many people here. Days 1 and 2 have been action-packed. I don't know about you, but I drank probably about a pot of coffee this morning. So I am rip-roaring and ready to go. My name is Jeff Johnson. I'm a software engineer on the GKE team in Seattle.
And I'm Tina Zhang. I'm a site reliability engineer for GKE based in London.
Today we're going to talk to you about delivering high availability clusters on GKE. This talk isn't going to go into a lot of details about what Kubernetes is. We're sort of expecting you to bring some of that experience in. Maybe you've used Kubernetes on GKE, maybe otherwise. But what we want to do is dive into some of the details on how we deploy Kubernetes, how we manage it. Tina's going to talk to you about how SRE keeps clusters healthy. And what I want to do is share some best practices in taking an application and making it resilient to zonal failure. So let's start with the K. If you have been around GCP Next this week, you've probably heard this word a few hundred times now, so this slide might be a little irrelevant. But Kubernetes is an open source container orchestration framework, originally built by Google and now in the open source community. It is based off our experience running containers at scale with Borg. Kubernetes can run on any infrastructure. It can run in the cloud as a hosted offering. It could run on-prem. But the important thing to know for today's talk is that Kubernetes is all about managing applications, not infrastructure. GKE is, of course, Google Kubernetes Engine. It's a mature product that has been generally available for 3 years now. Although, to be honest, I think it's 3 years and like a month. But to the significant digit, I think that's pretty good. If you're interested in following GKE, our updates, tips, and tricks, I recommend checking out the Google Cloud Platform blog. So with a little bit of that product background, Tina's going to talk to you more about GCP.
Thanks, Jeff. So let's say you've decided that GKE is the right solution for your workloads. A next key decision that will influence the reliability and availability of your application is how you deploy your GKE cluster across GCP locations. So at the moment, you have a choice of 17 regions and 52 zones, and these are expanding all the time. So regions are independent geographic areas, or loosely speaking, a campus of data centers that consist of zones. And a zone is a deployment area for cloud platform resources within a region. So between zones of the same region, you have high bandwidth, low latency network connections that you can typically expect of less than a millisecond in the 95th percentile. And from an availability point of view, zones should be considered a single point of failure, where it's a failure domain within a region. So let's take a look at how that works in GKE. So the most basic deployment is what we call a zonal cluster deployment, like the one pictured here, where you have a single master along with nodes all in the same zone. And when you run a Kubernetes cluster on GKE, we host the master VM in our own Google project, and you create worker nodes in your project. So in this mode, Kubernetes will mitigate against individual machine failures, but in the event of a zonal failure, such as an asteroid striking a data center, the entire cluster will go down. So in order to deploy fault-tolerant applications with high availability, you should deploy your applications across multiple zones in a region in order to help protect against this single point of failure. And that's what we call a multi-zonal node deployment. So in this configuration, GKE will distribute your worker nodes across multiple zones within the same region, though you have to have at least one node in the same zone as your master, and you cannot deploy nodes in a completely separate region. And if you're using cluster Autoscaler and your cluster contains node pools that have the same instance type, cluster Autoscaler will try to keep those node pool sizes balanced for you when it's scaling up in order to prevent against uneven distribution of node pool sizes across multiple zones. So this means that an asteroid strike in a single zone won't take down your entire cluster. And Jeff is going to describe those failure modes in more detail.
So let's look at a typical application deployed on GKE. So if we look at this diagram, we have that hosted master node in US Central 1F, and that's in a Google managed project. So it's actually a bit opaque to you as a user of GKE, but it's important to know what's there. And we have our nodes across 3 zones. So each one of those green boxes maps to a GCE VM. These little yellow checkered boxes above, that's representing your application workload. So in this case, we have a deployment. We have asking for 3 replicas of that deployment. And Kubernetes has chosen to spread them across these zones. So what happens when that asteroid strikes? So we've lost our VMs. They are offline, cannot be reached, but we've maintained the other set of machines. The other 2 failure domains there are happy and healthy, so they're able to continue to serve traffic. Instances that are running on those machines are going to be unaffected, but the Kubernetes master is regularly pooling and looking at the state of the world, and will make the decision to schedule a new pod. It expects 3, it sees 2, so it'll create a second. So in that case, we get our application back, everything is happy, but this is the lucky case, right? We were fortunate that the zone that went down, the zone that we had an issue with, happened to not be the zone our master node is in. So what happens if that master node goes down? So in this case, we still have those running workloads. They still are remaining on those healthy nodes, and Kubernetes is designed to sit in this as sort of a steady state. The nodes won't evict the workloads. They're only waiting to be told what to do, but they don't have anything new to do, so they'll sort of remain in that mode. Traffic can continue to enter the cluster. So if you're using the global load balancer, it's doing health checks on those down nodes and won't route traffic to them. However, where you will experience a problem is when you have internal services. So if you have an internal Kubernetes service that is in that downed node over there, that downed zone, the internal services may still try to route to that machine. And that's because the control plane and the master node are responsible for registering the endpoints that tell the services where to go. When I want to connect to Redis, it tells me, OK, this is a hop that you can go to that's available. And without the control plane up, I'm going to have a stale set of routes. So we see how a single node can be problematic and can result in sort of this state. But Tina is going to talk to you about how we want to solve some of that.
OK, so in order to eliminate the single point of failure that Jeff just described, you can use a GKE Regional Cluster, which is a product that became generally available in June. And with a regional cluster, you get a multi-master setup, where there are 3 masters in 3 different zones within a GCP region. So we have a load balancer that's sitting in front of these masters, and that serves as the endpoint that's used to communicate with the control plane. And by having 3 masters behind your GKE cluster, we help to eliminate downtime when one master becomes unavailable, either because it's become into an unhealthy state or because it's being upgraded. So when we perform upgrades of the master, we upgrade one at a time, so you don't get the downtime that you would experience with a zonal cluster deployment. And then when it comes to the nodes, you could still choose to have all of your nodes singly homed within within one zone, or you can use the multi-zonal deployment that's shown here, which works much the same as before. But of course, ultimately, if you have a multi-master setup and a multi-zonal deployment, that doesn't automatically mean that your application is high availability.
So that begs the question, what does high availability mean? I think when we talk high availability, a lot of times we jump towards solutions. We talk about putting load balancers and things like that, failover. But simply put, high availability means meeting some high SLO. In practice, that's some number of 9s that meets your business needs. And really, there's many ways to achieve HA. You could have, for instance, a highly available network connection that you buy from an ISP because they gave you a dedicated circuit that has an extremely high SLO. Or you could buy internet from a couple of providers and perform failover between them. When you're designing your application, to meet a high SLO, it's important that you understand all the pieces that make up that application and can understand where all the failures can happen. One way to split that up, and I think this works well for a lot of applications, but we'll say in the context of Kubernetes, is to break it up into these 4 layers: the control plane, the networking, the application, and the persistence underneath all that. We saw how a single zone cluster on GKE could go down with a zone and the failures that can happen. So it's clearly not a high availability solution. But as cluster administrators, it's our responsibility to ensure that our cluster, our control plane, is running in a way that supports that failover. Tina's going to dive into some of those pieces of the control plane, into the Kubernetes internals, to talk about how we manage that.
OK, so taking a closer look at what's happening with the components on the masters when you're running a GKE regional cluster. So here we're going to show you how they interact with each other in order to deliver this high availability control plane. So to start off, when it comes to the API server, these all work in active mode. So all the API servers are actively doing the work that's being assigned to them by the load balancer. And this is possible because the API server is a stateless component. So it doesn't matter which individual API server is receiving the request, but they only talk to their local etcds. But when it comes to etcd, things are a little bit more complex. So a group of etcd instances together is called an etcd cluster. And because etcd is a distributed key value store that's backed by a database, there needs to be leader election with a strict majority in order for write to the database to succeed. You might ask why here there are actually 2 etcd clusters. This is because there is a core etcd that has the kind of main Kubernetes objects that influence the functionality and the operations of the cluster. That's etcd0. And then there's a separate etcd1 cluster that's used just for storing Kubernetes events. So these events objects are providing an insight into what's happening inside the cluster, such as a pod rescheduling or a pod eviction, but they're not fundamental to the functioning of the cluster. And you can imagine that they probably quite high in number, so we keep them in a separate etcd cluster for that reason. And I want to spend a little bit of time delving into why we have 3 masters for regional clusters and not 2 or 4. And this is all related to how etcd reaches quorum in order to write to the database. So for writes to succeed, you need a strict majority. So i.e. 2 out of 3 masters must reach agreement. And with 3 masters, that means you can tolerate the failure of 1 master because the remaining 2 healthy instances are still able to reach quorum. So it guarantees that there'll still be a majority of the cluster that can continue to operate. However, if we only had 2 masters, you would still need both members to be healthy to reach this strict majority, so you wouldn't have any failover in that case. So it's worth noting that actually during the period in which a master is being upgraded or 1 master is unavailable, your cluster control plane remains available, but technically speaking, at that point in time, it's no longer a high availability control plane, because if there was a meteor strike on one of the 2 remaining masters, writes to the database would no longer succeed. So you can see from this example that having an odd cluster size doesn't change the number needed to reach a majority, but you gain extra failure tolerance by adding the extra member. So you always want to run an etcd cluster with an odd number of members. So by running an etcd cluster of size 3, this means that our control plane is tolerant to the failure of 1 machine. And of course, it makes sense to spread these across different locations. So for the other control plane components, the controller manager, the scheduler, as well as the cluster autoscaler, these all have their own elections, but they operate in active-passive mode. So only the leader is doing any work, and it talks directly to its local API server on the same master. There's also an add-on manager leader election, and this just follows the elected controller manager leader.
So that's one piece of the overall pie, right? Having a highly reliable control panel, or control plane. Panel's nice too. But the network is also a key piece of that. When we talk about high availability and failover, that often means load balancing. But when you're thinking about load balancing, it's important that that piece isn't its own single point of failure. Load balancing on GCP is not like a traditional HA proxy machine, backed maybe by DNS round robin or something like that. GKE uses network load balancing, a product that's available for you to use on GCE. That load balancing is backed by technology called maglev. Maglev, there's a lot of excellent papers out there that go into great detail, but essentially it is a non-proxying load balancer that's part of our software-defined network, and it's the same technology backing load balancing across lots of products in Google. So what this diagram represents are some of the fiber connections between GCP's data centers. So Google lays a lot of its own cable across the sea, and we run our network at a pretty low utilization. What that gives us is the ability to do failover. So let's say Godzilla pops out somewhere in the middle there and takes one or two cables down. We have headroom in the other connections to send the data. So we're ready to do those sorts of failover. That sort of redundancy and headroom is critical to have network reliability.
Okay, so we've talked a little bit about how the control plane operates in a high availability scenario. Let's delve into a bit of what GKE is doing for you under the hood when we create a regional cluster, and by extension, how you might go about bootstrapping a high availability cluster yourself. Because after all, Kubernetes is an open source project, and many of our users many of our Kubernetes users might choose to run their own high availability cluster directly on Google Compute Engine or on-prem in a data center. So Kubernetes the Hard Way by Kelsey Hightower does outline the steps of what you would need to do to roll your own high availability solution. We're not going to go into all of that today, but there's also the cluster lifecycle special interest group in the open source project that have developed a kubeadm tool that helps a lot with the bootstrapping of the control plane. However, even with those fantastic resources, you still have to do a lot of the higher level setup and configuration. Importantly, you'd still need to bootstrap your own high availability etcd cluster. And the steps are, again, pretty well documented by CoreOS, who founded the etcd project, but they're still fairly involved. And they include setting up additional firewall rules and SSL certificates between the etcd servers for communication, as well as setting up some sort of high availability proxy in front. And vital system pods such as kubedns, you'd also need to set those up to use autoscaling and anti-affinity rules to be distributed across multiple nodes. And Jeff is going to describe that a little bit later on. But once you have everything initialized, managing etcd clusters can be a significant complexity overhead in itself. And I think we in the SRE team and many others in the Kubernetes open source community have found this out the hard way. So historically, we've run zonal GKE clusters, so just with one etcd replica. We've had issues due to etcd crash looping after a restart due to a bug in write-ahead log reading. There was also a bug in the version of etcd we were using where the database size would become increasingly bloated and defragmented. And with regional clusters, we have the added complexity of leader election. So we had some regional specific etcd bugs where the etcd1 events were not garbage collected properly, and where you could have an etcd member lagging behind in database snapshots, so not being fully caught up with the rest of the cluster. So what we also found was that the steps involved in fixing an etcd replica that's part of a 3-member cluster is also a lot more involved than just fixing one etcd replica. etcd is also extremely sensitive to disk I/O, so in the open source version of this talk, we always recommend to not provision the resources too conservatively, because when etcd becomes overloaded, you really need that disk capacity. But don't just take our word for it. As I mentioned, there's a lot of KubeCon talks on this topic from us and also other people managing their own clusters. But with GKE, the good news is that the cluster creation process happens behind the scenes at a click of a button. And once your cluster is up and running, your friendly SRE team are responsible for managing the control plane components on your behalf.
So now that you have a little bit of background on the top 2 layers of the stack, what you get from using GKE, let's talk about the next 2. Let's talk about your application and the persistence. A reliable Kubernetes cluster is a table stake for high availability, but it's not a silver bullet. As an application developer, it's your responsibility to ensure that your application is deployed in a way that's ready to handle failure. Your persistence should be resilient to single zone failure. So on GKE or GCE, if you're using persistent disks, that means using a regional disk and picking 2 zones to do replication across. I'll show you how to do that in a bit. And if you're using other data services within GCP, such as Cloud SQL, you need to make sure that they're configured in a highly available configuration and support failover. Your application should be running in a mode that is ready for failure. So for instance, just like the Kubernetes API server, if you're running in an active-active mode, that means that any one of your instances are ready to handle traffic at any time. This is an excellent pattern for stateless applications, and it's generally very easy to just turn the replica knob up. But it doesn't work for a lot of other applications, especially stateful applications. So there are other patterns, such as active-passive, you can utilize. In an active-passive mode, much like our controller manager, you've got one instance that is doing all the work and a few that are sort of sitting idly by, ready to be summoned. That requires a lot more orchestration, and I'll show you how you can sort of achieve a little bit of that with a little bit of downtime by using Kubernetes. So with all of that background and a week of hearing the word Kubernetes, let's jump into a demo where we actually make some stuff fail. So if you've ever seen a Kubernetes demo, no doubt you have seen the guestbook. The guestbook is a bit of a toy app, but it actually represents a lot of common patterns seen in just about every application. So if you haven't seen the guestbook is like a ledger. You can write a message. Well, we've got some saved there. And it is persisted through refreshes. Good, it's working. But to really understand what's going on and apply this to your application, we need to look at the services that make up the application. First, I will, of course, reconnect to my GCE VM so we can show you. If you're interested in looking at the guestbook is in the Kubernetes repo, the main Kubernetes repo, under examples. And what I did was I took the YAML that's deploying it today, and I made a few tweaks to support failover. So let's look at how it's deployed first. So this is a bit of an eye chart here, so I apologize for that. But I'll sort of walk you through the groups here. The top 3 nodes, the top 3 pods are the front end. That's a serverless web application in a Docker container. It happens to be a PHP application. And I'm throwing no shade on that. That was my first language, besides English. And if you look, that far right column in the node section, those are across 2 separate nodes. The 3 instances are across 2 separate nodes. Those 2 separate nodes are deployed to different zones. Oh, that's down here. So we have one of those nodes in central 1C and one in central 1F. The next set of pods here is the Redis follower. The Redis follower is a read-only copy of the database. So the persistence doesn't really matter. It will get in sync with the leader when we ask it, when we query for it. So whenever we do renders of the guestbook, whenever we do views, we're going to ask those databases what the state of the world is. But when we need to do writes, we want to talk to Redis leader. The Redis leader is the center of truth. And that means that its persistence is really important. If a zone went down and we couldn't get the disk back from that zone, well, then essentially our application is in a state where it's not useful. But a bonus that we get by having those read-only replicas running on separate nodes as well is that if one of those goes down, in the meantime, while the leader is being rescheduled, we still have a full copy of our database. We can still do reads. We may just have to wait a little bit to do commits. So let's take this thing down. I want to make sure we take down the one with a Redis follower. So let's do a little watch. And that follower is on DG00, of course, sorry, leader. And that is central 1C. OK. So fortunately for you, I do not have the ability to actually shut down a GCE zone. I could see where that would be a concern as a customer. But what I do have is the Kubernetes API. And what the API lets me do is it lets me mark a node as unscheduled and then immediately evict all the workloads off of that. If you're playing along at home, you can run these same commands there. Drain is the one you want to start evicting the workloads. Or you could do a gcloud compute instance delete. The reason why I'm just evicting them right here is that it does take a little bit of time for that node to come down and then Kubernetes to go, all right, it's time to reschedule that work. And that's because it's also designed for failure. It's going to have some loops before it takes action. But we're in a demo. We want to see action fast. And while I blabbed over that whole thing, we can see the Redis leader was rescheduled. It's been running now for 38 seconds. Some of our other pods have been rescheduled, and the ones that were running on that healthy node that we didn't mess with have been running for 3 hours when I woke up this morning. And let's hope this thing still works. OK, that's a good sign. So this looks like a toy. This is simple. But what we've actually done here is we've taken down a machine in a zone. Let's focus on the Redis leader. We took it down on a zone. It had an attached disk. That disk contained the truth of our application. We moved it to a new machine in a different zone that was happy. We reattached that disk, and it came up in a span of a short period of time. Throughout that time, our application would have been accessible. We would have been able to ingress into our cluster. While that Redis leader was being rescheduled, we wouldn't have been able to make writes, but we can still keep our page up and healthy. And that's a trade-off that you need to make when you're considering your application deployment. This, by the way, isn't what you'll get if you deploy the guestbook. If you go to Kubernetes examples guestbook, that's not what you'll get out of the box. Let's look at some of the changes I made to make that work. So let's look at the front end. So the front end, as I mentioned, is a stateless application. It has this is the YAML section of the talk, so it might be extra hard to see. Oh yeah, it doesn't get a lot bigger than that. So it is a Kubernetes deployment with 3 replicas. And that's where you say, I got a bunch of pods, run 3 copies of it. Out of the box, Kubernetes doesn't make any scheduling guarantees about where those go. So it could just as well stick all those replicas on the same node. If you're relying on a high replica count to handle failover, that's really not going to cut it. That's just one piece of the puzzle. What you can do, though, is you can hint at Kubernetes. You can tell it what you want. And if we look at the bottom, the way I've done that is using pod anti-affinity. Pod anti-affinity either tells or hints at the scheduler to schedule your pods in some way. So if you dive down the tree a little bit here, we've specified the same metadata, the same app selector, app guestbook, to your front end. And we specified this failure domain key. that being this zone key. So this is where you are starting to think about what you want your application to be resilient to. This could also be a machine. And this will tell Kubernetes, OK, if a pod is already scheduled on this zone or this machine, try not to schedule another one there. The Redis follower is deployed in the same way. I'm not retaining its persistence across because it is able to catch itself up to speed. We could try doing that, and it should work, but if you don't need to make it that complex, don't. Let your testing and let your evaluation of the reliability inform those sort of decisions. One thing I want to point out, though, is that we've used prefer schedule. You can tell Kubernetes absolutely do not schedule this node if it's on those, if it meets these conditions. But what would happen in that failure scenario is when we lost a zone, sure, we'll move over the work that can be moved over, those like singletons. But we're not going to reschedule the nodes that you'd expect. We're not going to say, OK, well, let's shift all these leaders over here to this healthy zone. So we won't actually be able to serve the same capacity that we could before. It's important to be aware of this as you're planning your deployment. The most interesting one to show off is the Redis leader. The Redis leader is deployed as a stateful set. And I changed that from being a deployment. And what stateful set allows us to do here is specify a volume claim template. A volume claim template says, OK, I need a disk. And the disk has this sort of storage class, just a name, just a string that I picked here. And Kubernetes will reliably attach this disk, or attempt to attach this disk to my node, and eventually to my pod. So the volume I'm mounting is Redis data, and it's in the /data directory of the container. Nothing crazy. But the storage class is something that you're creating and you're planning. So let's take a look at how I define this storage class. For the storage class, you specify a name, a provisioner. So I'm using a GCE persistent disk, and then the parameters for that provisioner. The important ones to look at today are the replication type. We're using a regional PD, and then we're specifying 2 zones for that regional PD to replicate to. So regional PDs allow us to say, across these zones, I want to make sure that my data is always being replicated. So if I do a write here, it is always available in this other zone. These zones don't necessarily need to coincide with your VMs. But for performance, it's probably a good idea. And when you think about your exposure to failure, it's probably a good idea to be aware of that as well. All right. So now that we've seen a demo in action, let's sort of review some of those core concepts and best practices for your own application. Back on the slides. Thank you. So regional clusters are a piece of the puzzle to handle zonal failures. But they give you a lot of everyday improvements, like zero downtime upgrades and resizes. So something you should be aware of, if you resize your cluster from 1 worker node to 100, we're going to resize the master node backing that in our project. Because this is a lot more traffic, 100 nodes, obviously, 100x. And in that scenario, because we roll out changes one by one in a regional cluster, you shouldn't see a lot of downtime in that. That should be a graceful failover. As of GA, regional clusters are free. So there isn't really a concern about cost in terms of having a bunch of master nodes. But node locations are really something you should be aware of. And a reason to be aware of that is around cross-zonal traffic. So if you have an application that is particularly latency sensitive, that's doing a lot of intra-service communication, you might be used to that 1 millisecond in the 95th percentile timing, that sort of latency. But it's going to be increased when it's going cross-zone. Like Tina mentioned earlier, think of it as going out of one building in the campus and going to another. Another concern is cost of that traffic. So when you're running traffic within your zone, you're not being billed for that. But when you cross zones, there is billing associated with that. So if you're doing something like pulling down a lot of database results, if you're doing something like streaming a lot of log data, that can add up and is something you should be aware of as you plan your deployment. Technologies like Istio, like a service mesh, can help you to sort of inform these and plan these out a little bit better. A few things just to be aware of that are really more edge cases is that when you spread across multiple zones, you're exposing yourself more to zonal issues. The simple fact that you're in more zones means that you might be in that unlucky asteroid strike, right? Things like upgrades, creates, and deletes could be impacted by that. It will certainly take more time to roll those changes out because we do those one by one instead of in one shot. So if you have an environment where you're creating GKE clusters very rapidly, you should be aware of that, something like a CI environment. If you're running a big cluster, it's not a guarantee that you can spin up 500 nodes immediately or 1,000 nodes immediately. So you may run into quota limits, for example. So it's important, just like your applications are reserving for capacity and failure, that you also have some node capacity if that's what you're designing for. And at the moment, you can't migrate between a zonal cluster and a regional cluster, so it's a choice you have to make up front. So with that background, Tina's going to talk to you about how we keep these clusters healthy and reliable.
OK, thanks, Jeff. So we've demonstrated how the GKE Regional Clusters product can make your GKE cluster more reliable. So, well, how are Google engineers keeping their side of the bargain to help make the GKE system reliable? This is a challenge for us, particularly as the adoption in GKE continues to grow, as well as the number of GCP locations. So in the SRE team, we're responsible for managing the fleet of GKE hosted masters and making sure that the Kubernetes control plane components are up and running, as well as managing the upgrade cycle of the masters and ultimately protecting the service level objectives to ensure a positive customer experience for our users. So we do this by holding the pager for the product, but we also help to work with feature launches, the release process, and general product designs with our developer partners, as well as other teams within Google that GKE is reliant on. And we have teams in Seattle and London providing 24/7 on-call coverage. And ultimately, the aim of all site reliability engineering teams is to automate our own jobs away, much in the same vein as the Kubernetes self-healing philosophy, so that the system can detect and heal itself without manual intervention. And we do this by iterating on pages and outages to make sure that they don't happen repeatedly. So in order to do this, we need to have good observability and strong insights into the system behavior. So we care both about the GKE platform as well as every single cluster. And we do this by gathering metrics on both of those aspects and visualizing them on dashboards using an internal Google version that's been around for years, used by all SRE teams. But it's pretty similar to how you might use Prometheus or Grafana for metric gathering and visualization in your own clusters. And we also keep an aggregated view of this so that we can see fleet-wide differences between cloud locations and different Kubernetes versions. And finally, we have some probers running outside of Google Cloud Platform that are constantly creating and deleting clusters. So this helps to give us a critical black box view into what a user would see. So in order to gather this data in every cloud location, we have a job running outside of GCP called the monitoring server. And this collects metrics, metadata, and core component logs from each master. So our definition of master availability is based on kubectl component statuses returning healthy for every component. And if availability is down for a short period of time, the monitoring server will automatically recreate the unavailable or unhealthy master VM. And it can also resize the master VM in order to handle higher workloads. And if these actions don't work and the master continues to remain unavailable, an alert is sent to your friendly on-caller. This can also happen if some other metrics get into a bad state according to some predefined conditions, such as etcd backups being too old or master VM disks being too full. And depending on the severity of the condition, the alert can be either a ticket or a page that requires an immediate response. And it might be version-specific, location-specific, or even cluster-specific. And we can also get tickets from our frontline support team if they're seeing urgent customer issues. And I think we're pretty lucky in GKE that so many Googlers are contributors to the open source project. So when we do see issues or bugs with an underlying version of Kubernetes, we can pretty easily get those fixes in. So a common workflow might be an on-caller receives an alert. We would then check our dashboards and metrics to see the vital signs of the cluster, look in the playbook for mitigation and debugging tips. These might include some of the etcd bugs that I described earlier. And then we typically use one of the following common procedures to mitigate against problems. So rolling back or rolling forward, if it's a problem with the GKE control plane, that's pretty straightforward as we have full control of those jobs. If it's a problem with an underlying Kubernetes version, it's a little bit trickier. We would need to cut a release with a fix and upstream it. We can also upsize or upgrade the master if it's a cluster-specific issue. Typically, we'll try to give the master a few more resources, and in the case of higher workloads, that's pretty effective. Sometimes we'll have to tweak the alert if it's set too sensitively or if it fired in a way that didn't make sense. And this is part of iterating on our alerts to make sure that they're all actionable. And finally, we do sometimes have to resort to silencing alerts. We try to avoid this as much as possible, but sometimes it's down to an issue that we can't take direct action on. For example, if we need to wait for the next open source release, or if it's an issue where the customer has to go into the Cloud Console and fix the problem. So we've talked a little bit about the routine alerts and routine mitigation actions, but sometimes a large outage occurs, something completely unexpected, and there's a large impact incident. So what do we do in those scenarios? So in SRE, we follow a mantra of coordinate, communicate, and control with an established protocol in a crisis. So on-callers are encouraged to pull in other members of their team and get help and assign defined roles. So you have an incident commander who is managing and coordinating efforts, an operations lead, and a communications lead. So there are established communications channels that identify the impact and notify our customers. You may have seen some of these on our cloud page. There's also escalation paths to other parts of cloud, and also our developers who have their own on-call rotations for various subsystems within GKE and Kubernetes that they have more expertise on. And after the incident, it's really important that we write a postmortem, and even more importantly, we learn from the action items from the postmortem and execute on them to make sure that the incident is not repeated. And sometimes we even share some of these details with our customers, so the timeline of the incident, the root cause, and the action items that we're taking. So that's what we're doing on our side to improve the resilience of the system. To wrap up, as potential regional cluster users, what can you do to help improve the resilience of your cluster and also help us not to get paged? So in the open source version of this talk that I gave at KubeCon, we'd talk about ensuring that your etcd backups are done frequently and that you also test the restore from backup procedure frequently as well. But as I mentioned before, in GKE, this happens automatically for you. And similarly, if you're running your own master, I'd be advising that you upgrade frequently and keep on top of the latest security fixes. But again, this is taken care for you in our managed Kubernetes product. However, as a GKE user, you still have full control over the upgrade cycle of your nodes. And we strongly recommend that you enable node auto update so we can keep it in sync with the master version, as well as node auto repair for a fully self-healing cluster.
We also recommend that you're provisioning your project to have the quota and capacity to handle these multi-zonal workloads. Something you can do to help the Kubernetes scheduler out is to provide resource limits for your pods and allow it to schedule those a little bit more intelligently. As an application developer, it's important that you're aware of those high availability scenarios. High availability masters, regional masters, do not make your workloads high availability out of the box. Spread your pods across multiple zones and machines using pod anti-affinity, and ensure that you're using regional storage and data services. So we thank you all for joining us in this talk and learning about GKE. In interest of time, Tina and I are going to have to give up this room, but we're going to be available outside to answer any questions you might have. And otherwise, please enjoy the rest of the day. Thank you.